Now it's time for them to present their project presentation.
This is the project presentation on our project Landmine Detector. In this presentation, we'll be focusing on the problem we are trying to solve, the current situation with it, and what an ideal solution would look like. And we'll discuss how we approach the problem, the features we introduce, and how we manage to mitigate problems presently. And then we'll dig a little bit deeper into the project, talking about technical details and future improvements. Finally, we'll talk about budget and timeline to get an overview of where our current progression is at and where we'll be moving forward. Our team consists of myself, Karanayaka, HT Manohara, TTV, and Rupasinghe. We are a third year project group from the Department of Computer Engineering, University of Peradeniya. So landmines, what are they? Landmines are prone weapons used to destroy enemy targets. Often you'll find them underground, hidden, pressure activated, and cause devastating effects when exploded. The problem with these are that they can remain active even decades after a crucial conflict has ended. It is found out that military personnel as well as civilians get injured by these unexploded bombs on the daily basis. So, many countries as well as organizations have moved their focus onto demining operations. So, currently, the main way of these landmine detection process is happening is the humanitarian way, where volunteers use metal detectors and go to the search fields themselves and search for landmines. Alternatively, the use of animals such as dogs and rats have come into play, and more modern approaches such as remote control vehicles. So what are the problems with these approaches? Number one is the time it consumes. Since it's a manual way of doing things, costs a lot of time. Then cost in training the soldiers, volunteers, training the animals, and maintenance of equipment. So what should an ideal solution look like? First and foremost, it should be low time consumption and it should be efficient. It should have minimum human labor. Since there's a high skill requirement for manual humanitarian way and also some sort of a barrier when using remote control machinery as well. And the solution should obviously be lower cost than the current methods available. So what are the features we introduce? So obviously the system would have a landmine detection in it, and it contains autonomous navigation where it totally minimizes the involvement of human interaction with the system and gives a map visualization to get a better understanding of the area of how the landmines are spread out. And last but not least, we give the option of data store where we collect information and store it so that we could keep on updating when certain new improvements have been made. So implementation. The main overview or the flow of the system happens as follows. First, the user interacts with the user interface, where the user gets to input data such as the search area and other parameters to a backend. Then that data would be transferred to the robot, where the calculations would be done and it would carry on with an autonomous search. Here, it would search for landmines, detect obstacles, and detect cleared paths. These data would be sent back to the servers where a map visualization would be done at the user interface. Here's a very detailed view of the backend. What generally happens is that users get to interact with the user interface here, and they get to input data, the search area data or relevant parameters. And here, then the data gets transmitted to the robots from the servers through MQTT protocol or HTTP. And in the case where robots send back data, it would go through the same process, but here it would also, in real time, would display the information as a map at the user interface, and at the same time, store data at the database. So this is what user interface would initially look like, where you either can enter the information manually, or you could have the option to draw the shape or general area of the map. Then while on search, there would be a certain overlay over the map that shows landmine detected options and obstacles and cleared paths. So talking about the robot design, it's of three main parts: the communication unit, metal detector unit, and the navigation and movement unit. The communication unit is mainly consisting of a GSM/GPRS based communication, since communication happens on MQTT or HTTP. Here, the problems with network failure is handled by using MQTT with quality of service 1 at the server side. So that guarantees each message will be sent at least once. And on the hardware side, we'll be implementing some sort of a buffer, which queues up the messages that should be sent back to the server. So when the communication is reinstated, the process happens seamlessly. The landmine detection unit. The initial landmine method of detection is done through a simple pulse induction circuit. So to be more specific, using the Colpitt's oscillator circuit. Here we can change the frequency of the metal detector by changing the current through the inductor coil. Alternatively, we'll be developing as future improvements to implement things like ground penetrating radar and radio frequency based metal detection. So navigation is mainly done by a combination of the new item GPS module coupled with the GY80 IMU. These sensors are important in robot positioning, specifically the magnetometer and gyroscope, since the whole system is sort of a GPS waypoint based navigation system. These sensors are very important. The obstacle detection happens using ultrasonic sensors. Since this is an outdoor robot, we'll be adding the human humidity and the temperature compensation values for the distance values. Talking about movement, the whole system is a four-wheel drive method. So we'll be using four 12-volt DC motors with 150 RPM. The motors will be driven using a separate microcontroller for the system. Here, the feedback values would consist the encoder values from the motors in themselves and the sensor values from the IMU, such as the magnetometer, gyroscope, and the accelerometer. This is a very high overview of all the hardware components, main hardware components from the three parts of the robot. So here we can see that the node MCU is the main unit controlling the robot. And here we see that there's a separate microcontroller for the communication unit, SIM900A for GSM communication, and SD card, which is the buffer that I mentioned earlier. And here the separate microcontroller for the motor driver plus the interrupt handler for the metal detector. The budget as of now is around 28,440. This consists the ESP32, the 2 NML chips, and the 12-volt lithium polymer battery of 10,000 milliamps. The timeline is of 5 milestones. The first one we passed was doing research, trying to get an idea about the feasibility and how we can approach this idea. Second, we moved on with backend and hardware design. And third milestone, which we are currently at, we are implementing backend, front end, all the software components of it. And the fourth milestone, we will be implementing a first initial prototype of the system, the hardware system, and we'll be doing unit testing. And finally, at the fifth milestone, we'll have an initial base system. So talking about the project impact, in comparison with the ideal solution we mentioned earlier, this definitely mitigates the efficiency problem since it's autonomously done. There's no time wasted. And then we are handling the time consumption as well. Minimum human labor required since it's an autonomous search. And this definitely minimizes the cost since there is no cost required for training and some other sort of stuff. So with that, I would like to end the presentation. Thank you very much for listening.
Right. Thank you, contestants of team number 1. Now let's move on to their Q&A session. We'll first give the chance to our esteemed panelists to raise questions from the contestants, and then the distinguished guests and the other participants in the audience get the chance to direct their questions through the chat box. So we'll first move on to our panelists.
Hello.
Yes, sir.
Yes, Darshan here. So I just want to ask them that now I know that they said initially that what they're doing at the moment is like manually they're trying to detect it, and there are some autonomous vehicles. But I remember that there has been some work even previously. I can remember some very long years back also there were some attempts at autonomous vehicles and things like that. Have they looked into that devices, and if they have, I mean, why were they? I mean, why have they not worked in Sri Lanka? And if so, what are you doing that is different from those attempts?
Can you hear me, sir?
Yes, Akila.
Yeah. So yes, we have looked at them, and the certain things that we have introduced more here is like the opportunity. So we are initially building a system, whole system around it. So it gives us an opportunity to develop on it, so make improvements on it. And in this system, we have, like, as I mentioned, there's like a separate component for data storage. Like this whole infrastructure is built upon this process of demining, if it makes sense. Like it's not just
I think you're on mute. You just stopped it. Okay. So what is the? I mean, why did the previous solutions did not work? Is it because they were not a full product, or what was the reason?
I got cut off.
Ah, yes.
Yeah. Yeah. So we looked into them as well, but we decided that we could make some different changes, like in the method of detection and how we approach like visualizing the data and stuff like that.
Right. And
like, rather than pinpointing these positions in a like a more generic way, like giving out a buzzer sound or something, but giving in this case we are using like a map visualization, so that it would like give a very good overview of the whole area that's been searched upon.
Right. And one more thing, I didn't see anything in the presentation about the actual robot that you're sort of going to build. I think I saw a little bit of a design in the 3-minute video.
Yes.
Can you explain a bit about the robot itself?
Yeah, so we are trying to get the robot with an aluminum chassis and hopefully get some acrobatics panels for mounting and unmounting certain devices. But we haven't yet finalized all the necessary details as of yet.
All right. Okay. Thank you.
Akila, this is Ruan.
Yes, sir.
Yeah, Akila, I would like to ask, is there any reason why you didn't went into the like a drone? Because you had selected to go over the ground. Generally, landmines are pressure triggered, right?
Yes.
And is there any mechanism in your system to detect plastic explosive? And what would be the time of your equipment in the field? How long will it can operate in the field?
Okay. So for the first one, drones, yes, we have looked at it. Sorry, sir, you were saying something? Hello.
Hello, go ahead.
All right. So for the first question, yes, we looked into the drones, but after some discussion with the lecturers and all, we decided as an initial step, we should move on with the ground-based system, so we could get a field of it. And
what was the reason?
The reason, yeah. So hello. Yes. So The reason being, so first we really needed a better approach so that we could test out things rather than straightly jumping into a drone-based robot system. But given the current requirements, I believe that this is suitable enough rather than moving straight into drones. And the second question was, wait.
Plastic.
Yeah, plastic ones, no, not currently. That's why I mentioned in the presentation as well. So the base system that's currently being built is planned to be finished within the next 2-3 months. So in that time period, we are planning on getting that metal detector to work as a landmine detection device.
And the time in the field?
Sorry.
Time in the field, how many hours?
So time in the field currently with the battery that we are trying to occupy, it's like 1.5 hours. So it's limited by the battery capacity. And
yeah, that's why I wanted to check with you, because if you go for a longer time, your autonomous vehicle can create a pressure triggering system, right?
Yes.
So it will be very, very crucial in your situation. Please look into that part, how the autonomous vehicle can prevent the pressure triggering. And this would be a very good invention, Akila, if you can look into this one to develop. That's mean now you are trying to get to detect landmines after a war. In a war, if you can detect it on a field, right, on a drone, it will be one of the highly marketing equipment. You can sell it, right?
Yeah. Thank you.
Do we have any more questions from our panelists to the contestants of team number 1?
Hi, team number 1. I'm Samudaya.
Yes, sir. Please go ahead.
Yeah. Most of the question I had asked from the other two judges. So I have a couple of questions, like efficiency. So what is your moving parts of your robotic vehicle, and what is the covering area like width? So can you explain about like a performance of your detection mechanism?
Yeah, so we haven't really done like physical trials yet, but theoretically we are planning on a velocity of around 0.2, 0.3 meters per second. We haven't taken the speed as a primary evaluation thing for the robot, since it's autonomously done and it can be done in the background rather than someone waiting for it.
Okay, so you are planning to do like a straight line, like a single place mounted scanner, or it's that the scanner also moving horizontally while it's moving forward? So you are planning about that one with the detection accuracy and other things, because I want to know that the efficiency of your method. So any idea, because you are not yet implement, but you say plan about it?
Yeah, so the detection device is moving along with the vehicle. Is that what you're asking? Like, is it stationary or not?
Yeah, it's stationary in the single point to your vehicle, or it's moving in the what is called other direction, like when you are doing by the human, it's the person is moving forward, is moving both direction also, so it's a cover huge area.
Yes.
How about your design or your plan about that one?
Yeah, so the plan is to have an actuator arm at the front so that we could easily manipulate that as well.
Yeah, but then it's about covering width is limited, isn't it?
Not really. Well, yeah, because like even if it's done manually, you still have to go and cover first from, like, you start from one corner and you go for straight, right? Rather than going 360. You basically have to cover 180 degrees, like in your front space first. That can be done with the robot.
Okay, thank you. Okay,
thank you.
Okay, we've got a question from the audience. It's from Sabreez, and the question is how image processing technology is working here, and also it asks about the accuracy of your machine.
Yeah. So image processing is not done here. We don't have a camera or anything like that. Just manual sensors right now. Image processing is one of the discussed topics that's for the future implementations. But right now we are generally using manual sensors. And what was the next one?
Yeah, the accuracy of the machine.
Yeah, so the accuracy would be depending on the metal detector that we build. So right now the landmine detection is done using metal detectors set up to certain frequencies. That can be arranged in the robot. So that is like we can get that much of an accuracy, but we can't get that cannot be guaranteed until we test it out ourselves.
All right.
Thank you.
Thank you for raising the question, Sabreez. And are there any more questions?
Hello, I'm Sulochana.
Yes, madam, please go ahead.
Yeah. Team 1, first of all, congratulations, being selected as a finalist, and it's a good effort. One question, what is the autonomous navigation technique you are using? Are you giving GPS waypoints?
Yes, so the plan is like what we are doing right now is like we give a GPS coordinate based area. So the robot gets the details of the area that should be searched in the form of GPS coordinates. And then the robot actually does the calculations and starts searching in that area. And while on search, it usually collects data depending on the sensor values that it gets. So it keeps track of it, and at the real time, it sends back data to the server.
How about path planning? What is the algorithm?
We are currently testing a few since we haven't really come up to that part, but we are working on it right now.
And the other thing is, how about the collision avoidance?
Yeah, so the collision avoidance is mainly done through the ultrasonic sensors that we are implementing. And if it's detected, it would be registered in the system, so collected as a data point. That portion should be avoided. So once a search has started, that data is retained in the robot, so it can keep checking back with that data when it's on search. And since it's not going in such a high speed, it can have that time to calculate, that moving time to calculate the next possible path.
One concern in your claims, you said this is more efficient and low cost. Like we can just forget about the cost aspect.
Yeah.
How would you compare the efficiency now? As far as like I heard up to now, you don't have a working or a prototype or at least a simulation, right?
Mm.
So, I mean, what is your comparison? Is it with the manual exploration time, or what is your
manual
reference?
exploration time? Since there, what happens is mainly using like a team of volunteers doing the search manually. That time can be used in other ways, since using a human label.
Yeah. So, what is it quantified? Like how much area covered by manual methods? Right now, and what is your expected speed of exploration? So, do you have any estimation of that?
Yes. So
Hello.
Hello. Yes. Sorry. I got cut off. So yeah.
Yes, Akila, please go ahead.
I think he's losing his connection.
Can Tisarao with Vishu Navanjan can take the questions.
Initially, we get the coordinates of the location, and then we identify some area, and we are trying to clear that area also. And we have saved the initial location what we have given, and Robert while checking the area, Robert checks whether it has come to the initial point. Otherwise, he checks also.
Okay, so final remark from my side. I mean, this area is quite well established now, these autonomous vehicles and that navigation. There are quite a lot of algorithms. So I expected actually when I saw your project that you may have some feasibility study based on simulators. So these days, these robotic simulators are very, widely used. Even school kids, like young people, it's easy to use. Like platforms like VBot, you can simply configure a plane, a grid, and then try out one of the robot models and test it out. So I suggest like you can also quickly do a quick feasibility study with the available simulations and check for some algorithms. Okay, thank you.
Okay, madam. Thank you.
Yeah, I have one question based on Tisara's explanation. You said you will be clearing the ground before robot is launched.
No, sir. We initially give the coordinates of the coordinates, and there is a feature also. We can also define the area by drawing in the map, and while the robot is moving on the ground, he checks synchronously. He checks whether it has come to the initial point. Otherwise, he does his search because if there is a case of power failure or network failure, he has the coordinates. He has the coordinates of the initial point, and if there is a connection error or power connection error, it tries to come back to the initial point because there are it has saved the all positions. It has gone through the land.
Okay. My question is, this is for you to look into the efficiency of the system, because you will be moving into a ground where the vegetation has grown, right, over the landmine area, right? So your obstacle avoiding system might avoid the landmine also, which is the vegetation, right? So please see how you could improve that part of it. Thank you.
Okay, sir. Thank you.